So because you have y cubed in this case, you have to reduce it using Bernoulli's transformation to be able to solve this differential equation. Yeah.
You reduce that, and then you
So
reduce the other side.
You're gonna call v equals y to the 1 minus n, and n in this case is the degree of y. So this is n. So n equals 3. So that makes v equals y to the negative 2, which makes v equals 1 over y squared. Or let's just leave it as and differentiate it. So then dv over dx is equal minus 2 y to the minus 3 times dy over dx. And we're going to do the replacement in the differential equation. So that makes dy over dx equals, divide both sides by y to the negative 3, no, negative 2y to the negative 3. So dy over dx becomes minus 1/2 y cubed times dv over dx. And now we're going to plug and chug into the differential equation. So we're going to plug this there, and we will get minus 1/2 y cubed dv over dx plus y. So if v equals y to the negative 2, y is just
v to the would be v to the negative 1/2.
Yeah. So basically v is 1 over y squared. So y is square root v. So plus v to the 1/2 equals x times y cubed, and y cubed is just v to the 3/2 because y is root v. So cube it.
V to the negative
3/2. Yeah. Right.
Yeah. Well,
minus 3/2 negative because it's in the denominator. And as such, maybe we should leave these as y's for the time being for a moment before we start switching here. Be easier. So this is just plus y, and this is xy cubed. And now we're just going to divide everything by y cubed. And the y cubed goes away. And we get minus 1/2 dv over dx plus y over y cubed is 1 over y squared, which is the same thing as v. 1 over y squared is v equals x. So we transformed this differential equation into a first order in v. And now from here on we can go and solve it. Yeah?
Well, you said you got into a first order. How did you get rid of that? Because because v is y to the negative 2, so y cubed. So I like.
Watch. This is just algebra. This turns out to be negative 1/2 y cubed dv over dx. Because when you differentiate this, you get minus 2y to the negative 3 dy over dx.
Oh yeah. Dv over dx compared to dy of dx, or compared to.
Okay.
Wait, how did you? Wait, what? The
dy over dx. V turned out to be y to the negative 2.
yeah.
Differentiate both sides.
Differentiate. I mean with dv dx. I mean.
Yeah, dv dx, and then the right hand side y to the negative 2 becomes negative 2y to the negative 3 dy over dx.
Alright, so dv dx plus y to the negative 2. So dv dx. Well, I got dv dx to be negative 2y to the negative 3.
Yeah. Negative 2y to the negative 3 times dy over dx.
Yeah.
Okay, solve for dy over dx. You get minus 1/2 y cubed dv over dx. If you solve this for dy over dx.
Oh, wait, I see what. So.
Okay. And now we can write this in standard form.
Wait, what did after? So wait, where did you plug in? Where? Because I put I found dv over dx is negative 2y to the negative 3 dy dx plus v, which is y to the negative 2, equals x times y cubed.
You got this?
Yeah.
Divide everything by y cubed.
So that's y to the negative 3.
Which one?
And the dv dx. Because y.
How is it y to the negative 3? You're solving for dy over dx. You're dividing by y to the negative 3. It becomes y to the 3.
What are you dividing by? Oh yeah. You mean you divide? Oh yeah, divide the whole. I see what you mean. You divided the whole thing, the whole left side by y to the negative 3.
I divided the whole this side you mean here or here?
No, this side.
Everything by y to the third.
Well, then you would get 1 on the left side. On the right one, like plugging it in, I got.
You messed up with the algebra. Those are not right.
Well, it's dy dx plus y equals, and so for v, I put, oh, well, I just replaced it with v.
Wait. You can't just replace stuff. You have to replace consistently. We are replacing dy over dx from what we solved for us from here.
Right.
Okay. So, with that said, now this becomes, if we multiply by -2, we get minus 2 plus 2x minus 2v equals 4 plus dv over dx equals 0. And now this is the n, m, as a function of x comma v, and this here is an n, which is 1, and clearly the derivatives are not going to be the same. And dn over dx equals 0. They're not equal, therefore not exact. And we have to use the integrating factor method. With the integrating factor, we're going to multiply. So this is dv over dx plus 2x minus 2v equals 0. So we're going to multiply by an integrating factor here and an integrating factor here, no? And we're going to claim that d over dx of mu v will get us the above. So if we apply the product rule, we get mu dv over dx plus d mu over dx, no, times v equals 0, which means this has to equal oh wait, I was supposed to move this to the other side. Yeah, before I do this to make it easier, let me move the 2v here. Um, Okay. Yeah. Let's move the 2x here. So let me put it in the standard form first. So in the standard form, before I put the integrating factor, this is just dv over dx minus 2v equals minus 2x. No? Now this is in the standard form. Now I can multiply by my integrating factor here, here, and here. And I'm hoping that I can get a product rule out of this guy to equal this. So if I do apply the product rule, what do I get? G mu over dx. Alright, let's do the dv over dx first. So mu dv over dx plus d mu over dx times v, and as such this has to equal this for these two to be the same. No? So d mu over dx is to equal minus 2 mu. Separation of variables. Mu is my integrating factor. No. Integrate both sides. So ln mu equals 2x, which makes mu equals e to the 2x. Or with a negative. Don't forget the negative. Negative 2x. So integrating factor turns out to be e to the negative 2x. So now let's plug and chug. So that means d over dx e to the minus 2x, which is my integrating factor, times v, has to equal the right hand side of minus 2x times the integrating factor e to the negative 2x. No? And now I can just integrate both sides. And by fundamental theorem of calculus, this undoes that, and we get, because the integral of the derivative is just the function itself, and here we need integration by parts once. So if x is u, du is dx, and e to the minus 2x is equal to dv, so v equals minus 1/2 e to the minus 2x. Let me move this here. Okay, and now we'll apply integration by parts on that. So we have a minus 2 sitting outside, and x e to the minus 2x becomes uv, so that's minus 1/2 x e to the minus 2x minus the integral of v du. So minus 1/2 becomes plus 1/2 e to the minus 2x dx. And we're getting close here, so we get m plus c, of course. So e to the minus 2xv. Are you stuck somewhere, man? Is equal to x e to the minus 2x after we FOIL the negative 2 minus the integral of e to the minus 2x is e to the minus 2x divided by negative 2. So this becomes a positive 1/2. Plus c, and now we can divide both sides by v, by e to the negative 2x, so we get x plus 1/2 plus c e to the 2x. So here's our v. And now we've already claimed at the very beginning that y had equaled, or v was 1 over y squared. So that means 1 over y squared equals this here. So now all I have to do is flip it and take the square root, which could be plus or minus, by the way. Yeah. So y plus or minus. Are there any intervals in the question? Oh, y of 0 equals 1. Oh, we can find c then. So here, let's just use the initial condition. Y of 0 equals 1. So that means 1 equals 0 plus 1/2 plus c. E to the 0 is 1. So c equal minus 1/2. So that means y squared is equal to x plus 1/2 minus 1/2 e to the 2x, all raised to the minus 1, which makes y equals plus or minus the square root of that. If you're going to solve it explicitly, this is an acceptable answer. Or you could say plus or minus 1 over x plus half minus 1/2 e to the 2x square root. This is the explicit answer and this is the implicit answer. Yeah? Here we go. That does it. Interesting problem.